So welcome to Lecture 2A, which is entitled Limits and the Existence of a Limit. And this is just some background information before we actually get into some particular examples. There are three lectures in total constituting Lecture 2A, B, and C. So the material that's being covered here is from Chapter 15.2 of the text. And the objectives are to differentiate between axioms, definitions, and theorems, give you a little bit of a background, and determining the existence or non-existence of a limit for a multivariable function. Focus here being more or less on two variables. And what are the concepts and definitions? Well, what are the differences between axioms, definitions, and theorems? At least on a very preliminary level, because these are things that are important when you start actually looking at how to apply the axioms and theorems that are provided to you. Also, what do we mean by a multivariable limit definition? What is it? And then two types of problems we'll be looking at. One is determining the existence of or non-existence of a limit using the direct and contrapositive method, respectively. And so this will be a question of guessing, first assuming that it exists. If it does, you work through a certain process. On the other hand, if it turns out that it was a bad choice, then you go a different approach and you assume it doesn't exist. Note, the information on axioms and definition theorems is good to know about, but you're not responsible for this material. It just might give you a little bit of extra information that's helpful in terms of understanding what we mean by definitions, axioms, and theorems. All right, as usual, the second slide is just the outline of this particular lecture. And so there are 5 items that will be covered. First will be the axioms and definitions and theorems. That's our starting point. Then we'll basically define in the most primitive sense what is the definition for a multivariable limit. Next will be the definition of boundary points and interior points, followed by the definition of open and closed regions and sets, and also methods finally for determining the existence or non-existence of limits. Okay, so this is the only slide you're going to get, more or less, sort of trying to introduce the notion of what we mean by axioms, definitions, and theorems. And of course, there's some confusion out there in that we sometimes use axiom definition interchangeably, which generally speaking can be done, but to be clear, an axiom is a statement which assigns a truth to statements. We build mathematical theorems around axioms. Definition, on the other hand, is a label that gives names to objects with specific properties. So for the purpose of this course, the terms definition or axiom can be used interchangeably. So just not to confuse things. So the main point is that a definition or axiom is always a biconditional statement. And a biconditional statement is generally written as an if and only if statement. And if you put it in codified form, then it would be if P, where P is something that you want to state, then Q, and if Q, then P, right? That in combination basically is an if and only if statement. And putting it in simple terms, we would have P with a double arrow, Q. The theorem, on the other hand, is a conditional statement, but sometimes it can be a biconditional statement. It's written as an if and then statement, or as if P then Q, and it's one direction, which means P to Q. So that's the symbology we would typically use. So let's take 2 simple examples to show the differences between a conditional statement and a biconditional statement, such as a definition or an axiom. A conditional statement basically could be something of the following form. If you live in Toronto, then you live in Ontario. Okay, that statement is true. I've basically color-coded the ifs and thens throughout so that you can see there's something sandwiched between if and then, and that's something that basically comes after then. So the 4 things that we would look at would be, for instance, the conditional statement, which is in fact the statement as provided to you at the outset. And so we would say if P would represent to live in Toronto and Q would represent live in Ontario. All right, let's see if there's a truth to the inverse. The inverse is where you negate what is after the if, and you negate what is after the then. So this would mean that if you don't live in Toronto, right, then you don't live in Ontario. Of course, that's a totally false statement. So keep that in mind, because we'll see at the end the reasoning that we take when we talk about proving theorems. What is the converse? The converse basically is working backwards, starting at Q and working at P. So if you live in Ontario, which was PQ, then you live in Toronto. Well, that's also false, because you're not obliged to live in Toronto. You could be any other place in Ontario. Right? So you got two falses. The contrapos, on the other hand, is quite different. In this case, basically, you negate both, but you change the order. So it's more or less like taking the converse and then basically an inverse on it. So if you do not live in Ontario, then you do not live in Toronto. That's a true statement. So if you have a conditional statement, then the actual conditional statement or the contrapositive basically are both truthful statements. Okay, that's very useful to know. Now, if it's a biconditional theorem, then of course the situation is quite different. And of course the definition and axiom would be biconditional by definition. So let's take that as an example. If it is a triangle, then it has three sides, or alternatively, it is a triangle if and only if it has three sides. If to be absolutely rigorous, given that a biconditional statement is an if and only if. But quite often they don't even do that. They'll just say if and then. So just keep that in mind. If it's conditional, which is our starting point, we said if P is a triangle, then Q has three sides. The inverse would be to negate both. So if P is not a triangle, then Q does not have three sides. That is a true statement. Converse basically would work, is going backwards, starting in Q and moving towards P. So in that case, if it has three sides, then it is a triangle. That's a true statement. And the contrapositive would be basically like taking the converse and then inverting it. So that would basically say, if it does not have three sides, then it is not a triangle. That's also true. So in a biconditional statement, all of the conditions are true. That's items 2 through 4. So it doesn't matter which way you go. It makes no difference. So this is something that's really handy to sort of keep in mind when you start looking at axioms, definition, theorems in terms of, how to approach the problem as a whole. All right, so now we get to what we mean by multivariable definition. So definition, basically we're talking about something which is a biconditional statement. And so I've just written it here. The function has a limit L, some value, as Pxy approaches some specific point on the xy plane, location AB, and written typically in limit form as shown there. If for any epsilon greater than 0, there exists a delta such that the absolute value of the difference between the function and the limit is less than some epsilon, whenever xy is in the domain of the function fxy, and 0 is less than the absolute value of the magnitude of p0, which is less than the square root of x minus a squared plus y minus b squared, less than delta. And so if you look at the diagram below, let's take an example here. In a 1D case, when we talk about the limit, we would have x minus a is less than delta. That's the absolute value, which means that every value between here and here basically is acceptable. And what you're doing is you're converging on the point of interest, which would be in this case in one dimension, x approaching a. However, with two variables, we're talking about a plane. And so the difference here is you only approach from two directions. Okay, simple problem if it's only one variable. But here we have an infinite number of possibilities, because you can approach from any point towards the point of interest on this plane in all possible directions. Here there are only two directions. Here, infinite number of directions. And so what we're doing here is collapsing this radius of the circle until we finally zoom in on this little point here. That's what this delta represents. If you look at that in terms of the limit itself for two variables, then it's the picture that you see on your right. So what you see here is this plane z equals L plus epsilon, and z is L minus epsilon. That comes directly from this expression here, the absolute value. So as epsilon goes to 0, then these two plates basically get closer and closer to each other and presumably converge on a single point if the limit L exists. And of course, we're talking about the range, the domain as being everything within the circle, and we're moving in every possible direction from any point within this circular region to the point of interest at AB. Right? And so this is the picture one can use. So you can extend this to more than two variables. So for example, for a three-variable case, right, the only thing that would differ would be the fact that the function now has three variables. And when you look at the distance that you have to go, on the xy plane from some arbitrary point xyz to the point of interest ABC, in that case, basically, you would end up basically at the norm or the magnitude being the difference of the components squared, summed, square root. You can extend it to higher dimensions you want, but this is the general approach taken when you compute limits. Of course, this is the definition. If all other techniques fail, this is the only approach you can take, and even this might be extremely difficult in terms of the application. All right, if you want to look at a sort of a interactive version of it, you can go to the link that's shown above. You just click on this, and you can play with this object and sort of see for yourself what's going on as you make adjustments. All right, so just for curiosity's sake, in practice, we need a functional relationship between delta and epsilon, and to prove that a limit exists. But this is in most cases very difficult. Note, most of the proofs that make use of the general definition use inequality identities a lot. The textbook, pages 931 to 932, shows some simple examples. If you're interested in knowing more about delta epsilon proofs, we're not going to be using them here, and so I wouldn't put too much time and effort in unless, of course, you're very interested in knowing more about it. Instead, we're going to go with some sort of simple techniques that would work under limiting conditions. At least it gives you some understanding as to, how to approach the problem. All right, so now we need to introduce two new definitions. One of them is what we mean by boundary point, and the other one what we mean by interior point. And so these three diagrams basically help us understand what that means. So on the diagram on the left, we basically are showing for the two variable case that you have to approach a particular point P0 from all possible directions, which of course will be an infinite number of directions. And in all cases, its limit should be the same. In other words, the limit should always be L. So limit exists if the limit is the same for all possible paths. Right. Now, if you look at this particular diagram, there's a dotted blue line on the outside. And this one we're going to be referring to as an open set, and we'll have more to say about that in the next slide. But the fact is that we're not including the boundary of this circular region, we're excluding it, hence we're showing it as a blue dashed line. All right, then we make the distinction between an interior point and a boundary point. So an interior point would be if you draw this small circle around the point P, and basically take the diagram on the left and repeat it here. You approach the point P within the interior region from all possible directions, and you should get the same limit. On the other hand, if we're dealing with the boundary point, that would mean on the periphery of this, pinkish region, then we basically would approach the point Q on the boundary, but only within the domain, which means that if you look at the diagram on the far right, you can see that you can approach the point P0 so long as you remain in this pink region. You could also, in the case where you have a solid line, which means you're including the boundary, then you could actually go along that boundary and approach the point P0. If this were a dashed line, then you could not include the boundary in terms of approaching the point P0. And again, the limit will exist if for all possible paths, you achieve the same limit. All right, so now we come to the notion of what we mean by an open and closed region, or closed sets. So that's by definition, we'll say it's open. A region is open if it consists entirely of interior points. and it's closed if a region is if it contains the interior points and the boundary points. And the examples that I'm going to demonstrate below can all be found at this particular link. So I'm going to make the case that this is a closed set, this is an open set, this is an open set, and this is an open set. This dark gray spot that you see here is basically just an aberration. Ignore it. It's part of this gray region as a whole on all 4 diagrams. You'll notice here there's a black dot, and here it's open. There's nothing there. There's a black dot. It's nothing there. Here basically is a black line around the boundary. No black line here, no black line here, and a black line around the boundary. So I said shaded gray are interior points. The black dot we'd call a boundary point, and the black line consists of boundary points enclosing the interior points. So these basically a series of points basically on the boundary itself. All right, so an open set is a region that does not contain any boundary points. The closed set is the union of the open set and all boundary points. All right. So for instance, if we look here, it's a closed set. Why? Because you have the boundary points on the region and you have the boundary point at the center, and you're putting the two together, so this is a closed set. In this case, we're not including the boundary here, and we're excluding the point at the origin. So this is an open set. Here, similar situation. Here we do have a boundary point, so we're including the point at the origin, but we're not including points on the boundary, which is the circumference of that circle. So this still remains as an open set. And this also is an open set because we do include the boundaries on the periphery, but we're excluding the point at the origin. So that's an open set. Now, what about the case of the XY plane? If we consider region to include all space in the XY plane, then the boundary of the region would be at infinity, but there is no definition as to what this means. So we consider this region as an open set. All right, so here's some practical approaches now in terms of what we're going to be looking at, given that we're not using delta epsilon method. So what we want to do is make the problem manageable by reconstructing the functional expression that you're given. So the resultant expression consists of polynomials or well-known functions for which one can show that the limit exists or does not exist. So let me just give you some examples. So something called the direct method, which is, for instance, you've got to prove the existence of a limit, all right? And so how would you write such a statement? Again, this would be a conditional statement. And so you can see the if and the then right here. So if the limit of A exists and the limit of B exists, this is just an example, then for specific types of operations performed on A and B, for example, the summation, the resultant limit also exists. All right, so this would be a classical way of a direct method in terms of the way the problem is formulated. All right, let's take another example, direct method. So for instance, here would be prove that for every path to a boundary point, the limit remains the same. So if I were to write this out in a classical if and then statement, then I would say, if the limit exists, then for every path to a boundary point, an infinite number of paths, of course, the limit remains the same. Okay, so immediately you would look at the fact that, well, how am I going to show that, I've considered all the possible paths? It's an impossible problem. Well, it's a conditional statement. So we could basically use the contrapositive approach and rewrite it, and it turns out if we do it this way, it's a much easier problem to solve. So again, in case of the contrapositive, we're looking at proving the non-existence of a limit. It's the negated. So that means you have to take the end, negate it, take the beginning, negate it, and turn everything backwards. So in this case, it will be if the limit of a function for a particular path to a boundary point is different than the limit of the same function for a different path to the same boundary point, then the limit of the function does not exist. That's a much easier problem to solve because all you need to do is to show that for any two paths, you get a different limit. You do not have to consider infinite, just pick any two. That's a simpler problem to solve. Okay, so that's basically the approach we would take if we sort of think that the limit does not exist. Okay, and it's always a question of making sure that the left-hand side is the calculable side, which allows you then to basically make use of the theorem, either be it contrapositive or direct. So just a couple of notes. In this course, we don't assume you have a formal training how to set up a proof, so we only provide you with what is relevant for the course. So in mathematics, the problem is to state the claim in a form which makes it amenable to applying one of the formal proof methods. You can refer to the document Introduction to MAT291F and the following link if you want more information. It's not mandatory reading, it's there only for your interest. I think if you were to just look at this table, it will suffice. And the second statement, note the statement after the if and before the then should be calculable. In other words, it's the part that you need to know. Okay, you absolutely need to know. If you don't know it, then basically you can't use the conditional statement in that form. It should be else consider reformulating the theorem, and that means typically a contrapositive argument might actually give you something which is calculable. And the third thing is, for the most difficult problems, you may finally have to work directly from the definition of limit. You may not have a choice. Okay, so we will look at some practical methods in terms of applying different approaches to prove either the existence or non-existence of limits. So I've just written them down here. So one would be what we call the basic limit laws. Basic limit laws are, addition, subtraction, multiplication, powers, and so on. And here we apply the direct method. These are specific theorems. Another approach is called factoring a numerator. This is also a direct method. Again, these are things we'll be discussing in Lecture 2B. Another approach is to multiply by an algebraic conjugate. This is also a direct method, also in Lecture 2B. We can also use the squeeze theorem, which you've learned last year. It's not covered in this course, but if you look at the note below, it tells you how it would be applied if you're dealing with a multivariable problem. So effectively what you're looking at is for two functions that basically bound the function of interest on the bottom and the top, right, and have the same limit. And then you can show that because of that the limit of the function of interest is also the same limit. You cannot use the squeeze theorem to prove a limit does not exist. We're not going to go there because, unfortunately, this becomes a game of guessing. You need to pick two functions which basically satisfy these conditions. There's no real sort of tested method for doing it. It's all case by case. Okay, and then the fifth is the change of variables. All right, and you can basically apply the direct method to prove it exists, or the two-path test, the contrapositive method, to prove it doesn't exist. Again, we'll do examples for both cases. And so the second part, which is a contrapositive method, prove the limit does not exist, we'll look at examples in Lecture 2C. So what's the general problem-solving strategy then? Is to make a decision if the limit exists or does not exist, which means you take a guess. And then apply one of the methods above. If you make the wrong choice, you will realize it pretty quickly. All right, so that more or less concludes Lecture 2A, and thank you for listening.